in this video, in computer networks, we are going to see about the protocol, network layer protocol, IPv4 version 4. In that, how classful addressing is considered. So that part we are going to learn in this video. These are the references. So in IP version 4, this is Internet Protocol version 4. And it is one of the 4 network layer protocol. This is the first version deployed. So version 4 is the first version that is deployed for use, wide use. It enables internetworking at the network layer. And it is a connectionless protocol. It doesn't provide any guarantee for its delivery. So it tries its best. So it is a best effort delivery model. And it mainly considers logical addressing. How uniquely a computer is identified in the complete network. Okay. So for that we need a special addressing mechanism. For that we are going for IP addressing, also known as logical addressing. And IP protocol along with the routing protocol also considers routing. So now we shall see how this IP addressing is mainly done by this IPv4 protocol. An address, IP address, is an address that has information about how to reach a specific host. Host here means a computer. And within a LAN means we can easily identify just the MAC address is enough. But outside the LAN means necessarily we need IP address. Then only we can identify that particular host. So this IP address is 32-bit unique address. So 2 power 32 combinations we can have. So the address space will be 4, 294, 967 and 296. This is a very big number. So those many addresses we have. And we can also call this as logical address or sometimes net address or network layer address. So in different ways it has been called. So IP address is represented in 3 ways, but the common way is dotted decimal representation. So binary representation is 32 bits, all 32 bits in zeros and ones form. Dotted decimal representation means each octet, okay, so the combination of 8 bits is converted into decimal value. So that is called dotted decimal representation. So each octet value, if all bits are made as 0 here, then 0 is the lowest value. If all bits are made as 1 here, and that value is 255. So that is the highest value. So between 0 and 255, we can have the number. And in sometimes it has been represented in hexadecimal also. So each this octet contains 2 hexadecimal digits. So totally 4 into 2, 8 hexadecimal digits we will have. 4 octets, 1, 2, 3, 4. 4 octets and 8 hexadecimal digits. So in binary, 32 bits. 88 bits grouped into one entity. Okay, in that way we will represent the IP. So we could say as IPv4 address is a 32-bit address that uniquely and universally defines the connection of a device. So here we should remember this word, connection of a device, not a device itself. Because one time If I am connected to my home network, different IP address is allocated. The same device, if I am going to my college or office, there I am using the official network, another IP address is allocated. So the IP address represents the connection of a device, the interface. Okay, it represents the interface in the network, not the exact device. That particular IP address is not bounded to my computer or laptop or something. Okay, so the connection, that connection is having that address. Whoever is bringing their laptop and connecting into that, that person will have that address. So the connection is having that unique address. So in IP addressing, we have two categories, classful addressing and classless IP addressing. So today in this video, we are going to cover classful addressing. Okay. In classful addressing, the whole 32-bit address is divided into 5 classes: A, B, C, D, and E. So binary notation, decimal notation. In both ways, we can have which part is coming under class A, which is coming under class B, like that. So for all these 5 categories, how the division is made. So this is how. All the addresses that are starting with first bit 0 are coming under class A. So totally 8 bits are there in first byte. First bit is fixed 0. All the addresses that are starting with 0. And remaining 7 bits, I can change anything. Okay. So if I give 2 power 7, that will that will be 128, 2 power 7. So we have 0 to 127 as the decimal value. Okay. So the addresses in decimal representation, all the addresses that are coming in the range 0 to 127 are considered as class A. In binary representation, all the addresses that are starting with the bit 0 are class A. Now, class B. Class B addresses starts with the bit 10, 2 bit fixed. Remaining 6 bits, I can change anything. Okay. So, if I change all the remaining 6 bits as 0 and this first bit only 1, then we will have the value 128. And all the 6 bits are made 1 and first 2 bits 10, then that value is 191. So all bits are 1 means that is the maximum value. All bits are 0 means that is the minimum, lowest value I can represent. And class C 110, class B 111, class E 4 ones. So this part we can remember. So once again, class A starts with 0, class B starts with 10, class C starts with 110, class D starts with 111, class E starts with 4 ones. So if you remember this, then filling the remaining bit, all zeros means this first division will come. All ones here means then this second range will come. So in that way, this part we can easily identify. Okay, or even for quick calculations, you can remember this range also. Okay. So how the address space, the total address space, like we have seen these many IP addresses are there when we use 2 power 32. So how it is occupied? So first bit fixed 0, remaining any combination. So those many addresses. So half of the addresses are coming under class A, 50%. Remaining 50% that are starting with 1 or divided or shared among B, C, D, and E. So in the next category, starting with 1, in that the next bit 0, all these are coming under class B. So half of that, 25% is class B. And next, in that remaining 110, so that is 12.5%. And in the remaining 6.25%, another 6.2%. So in that way, it has been categorized. Okay. So this is the occupation of each of these classes. So in class A, prefix value, that is network prefix. Okay. So this prefix address represents the network. Suffix part represents the host. As I told, not exactly the device, the connection. Okay. So for class A, first 8 bits are prefix, remaining suffix. So first 8 bits, based on that we calculate 0 to 127. For class B, first 16 bits are prefix, value 128 to 191. And for class C, first 24 bits are prefix, remaining suffix. So only these 3 classes are allocated for hosts. Remaining 2 classes that have least occupancy here, you can see, and they are reserved for different purposes. So class D is reserved for multicast address, class E is reserved for future bits. So these are not applicable for assigning to a host. These addresses are not assigned to any host. Okay. Now, so we shall find the class of the address. So if something is asked like this, so the complete 32-bit binary notation is given. So how do we find the class of the address? So we have to look into the first few bits. So the pattern is matching with 110. So we could guess 110 is belonging to which class? 110 is belonging to class C. Okay. So this is a class C. Now, in decimal notation, 227.12.14.87, if we have to find the class of the address, then 227 is coming under this group, where 227. So we could conclude that it is a class B address. Now, as I told, in every IP address there is a hierarchy. Two categories. First part is prefix, second part is suffix. Prefix, first n bit represents the prefix. Remaining 32 minus n bit represents the suffix. So this prefix denotes the network. Okay, so if I assume this is a complete network, then prefix represents the whole network and suffix represents the exact connection. Okay, as I told, the interface or connection to a host. So we should remember that. So this prefix is known as net ID, suffix is known as host ID. So as we have, this is similar to this analogy, student's roll number. So we have different parts in the roll number. This is the actual serial number of the student. This is to represent regular student or lateral entry. This is to represent the department, short form, and this is for the batch entry here. So likewise, in the IP address, we have parts. Based on that, we can quickly identify this IP address is belonging to which network and which host. So ID identifies the network. Host ID identifies the host on the network. Okay. So this is the complete view. Class A, first byte is for net ID, remaining for host ID. And class B, first two bytes are for net ID, remaining host ID. For class C, first 3 bytes for net ID, remaining host ID. And D and E are not reserved for host, so no segregation. Okay. So this is a complete consolidation. These are the leading bits and net ID bits and host ID bits. Number of networks. So this we could do. So net ID bits 8. So 2 power 8 networks we can have. But in that, first bit is fixed, 0. That we cannot change. So only 2 power 7 bits we can change. So 2 power 7 number of networks we can have in class A. That is 128. Then in class B, that starts with 10 in binary. Number of net ID bits 16. So 2 power 16 networks we will be having, but first 2 bits are fixed, 1 and 0, that we cannot change. So remaining 14 bits only we can change. So 2 power 14, those many networks we can have. 16,380. And similarly for class C, totally 24 bits for net ID. So 2 power 24 networks we are supposed to have, but first 3 bits are reserved, so only 21. So 2 power 21 number of networks only we can have. So this is the number. And addresses per network. So host bit ID is 24. So 2 power 24 combination of hosts we can have. And here host ID is 16. 2 power 16 different hosts we can have in each network. Okay, so here we are having 2 power 14 networks. In each of this, I can have 2 power 16 addresses for host. And here it is 8. So 2 power 8 different hosts we can have. So we could see class A network, limited number of networks are there, but each network is having many addresses. And class B, moderate number of networks are there, and each is having moderate number of addresses. And in class C, we have many networks, but each network is having small number of addresses. Okay. So for each of this, if we exactly write the start address and end address, it will come like this. So this table you can have as a reference. Now, so if the following binary IP addresses are to be converted into dotted decimal notation, so we have to convert byte by byte. So each byte to be converted into decimal. Then we have to write the dotted decimal notation. So binary to decimal conversion we should do. So how do we do that? So each octet we should consider from the LSB side, 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, and 2 power 7. So 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4, like that. Okay, so this also we can quickly remember. 1, 2, 4, 8, 16, 32, 64, 128. So now, if this is the binary form, 128, this portion is valid, and then 0, 0, and this portion is valid, and this portion is valid, and this is 0, and this is valid, and this is also valid. So I should add 128 plus 16 plus 8 plus 2 plus 1. Okay, 128 plus 16 plus 8 plus 2 plus 1. That will be the decimal number, 155. So, in that way, if I convert all the binary values, then I will get 129, 11, 11, 239 for the first. 193, 131, 27.255 for the second. Remember, the highest value in one octet will be 255. 256 is invalid. Okay. Now, if this decimal notation is to be converted into binary, so each octet I should convert into binary form. So how do we do that? Decimal to binary conversion. So normally we can follow this continuous division by 2. That also we should do. And for each division step, we should note down the remainder value. Okay. Then finally, the reminders are to be written from the bottom to up. So then we will get the binary form. 100 0 111 00. Okay, for the sample value 150. In another way, we could say 156. So the combination of values if we put, in what way it is coming 156. 156, 6 is the even number. So the last bit will be 0. So we can start with the highest value. 156 is larger than 128, so I can use this bit. And 128 plus 64 crosses 156. So I am not using this. And 128 plus 32, that also crosses 156, so I am not using this. 128, 16, yes, I can use that. So if I use that, I will get the value nearer to 156. So how many insufficient? 8 can I use? Yes, I can use 8. Yes, then 4 can I use? Yes, I can use 4. Okay, that's all. I got 156. 128 plus 16 becomes 144. 144 plus 8 becomes 152. 152 plus 4 becomes 156. That's all. No need of anything. 100, 111, and these two are not required. So in that way also we can convert. So we can convert all these decimal octets into binary in the same way. So this will be the answer. You can cross verify. Do it on your own, have a practice, and you can cross verify. Now, find the error if any in the following IPv4 addresses. So we could see first address 111.56.0.45. Now 0 we should not mention here. Okay, leading 0 is not having any meaning here. So that is not a valid IP. Now, next one. 221, 34, 7.8. Only 4 octets are required. This is extra. So this is also not a valid address. 75, 45, 301. The maximum address is, the maximum value in each octet will be 255. So 301 is not at all a valid value here. So that is wrong. And here there is a mix-up of binary and decimal. So that is also wrong. Decimal means completely decimal. Binary means completely binary. Okay. And even in binary, we don't have dots. So now that is the solution. Now find the class of each address. So if it is given in binary, then we have to check the first few bits. So it is starting with 0. So surely it is a class A address. The next, it is starting with 110. Okay, so 110 means it is class C address. So here it is 14. 14 is coming under 0 to 127 in decimal. So class A address. 252. So that is belonging to class E, the last value. It is very closer to the maximum value 256.